Okay. All right. So now we're going to continue. So we have the last rule, right? One more rule. 7. If you have two complex molecules, then it may have many branches, right? So if you have that, it's going to be sometimes super confusing, like how to number for the parent and what going to be the branches over there, right? So number 7 is the rule at that condition. If it is complicated, if you have too many branches over there, how to know which parent we're gonna label there, right? Let's see one example on the left. So you have so many different ways of choosing the branch, right? Of course, one gonna be the red one. So the bold line one, this can be one parent chain, right? In that chain, you have other branches. You have branch at 2, branch at 4, and 2 branches at 3. If you choose that, okay? If I choose the other one, let's say the black number over there. So if I choose that, 1, 2, 3, 4, 5, right? So at that condition, you can have 2 branches at 3, right? Branches, you have branch in branch 2, right? So that is another one. If you do the other way, remember you have up to number 5, right? So I can do number 1 over here, number 2 over here, number 3, number 4, number 5. I can do that too. I have the same number of carbon, right? So I can also do, let's say with a different color, let's say purple, okay? I can do 1, 2, 3, 4, 5. I can also do that. You have many possibilities there, right? So maximum carbon number is 5. So I have the 5 carbon chain, right? So I have different parent possibilities in this model. Then the question is which one is correct, or which one you're going to choose, so that's going to be easier to name that. Right? So we're going to avoid any complications. So we're going to simplify that. So I'm going to choose 1 so that I'm going to have as many branches as possible. That's the one you're going to choose. Okay? So let's see different possibilities. If I choose the red one, how many total branches I can have? 1 at 2, 2 at 3, 1 at 4. So I can have 4 branches if I choose the red. Okay? So if I choose the red, I can have 4 branches. If I choose the black number 1, how many branches you can have? Can you count? 1, 2, right? So I have 2 branches there. If I choose the green one, so how many branches are going to be there? 1, 2, 3, right? 1, I can have 2, and then 3. I can have 3. I can have 1 branch over here, so this is going to be 1 branch, right? And then other branch is going to be at 3. I have 2 branches at 3, right? So 3 branches is going to be the total. What about the purple one? So how many branches if I choose purple? So I can have 1, 2, 3, right? So I can have 3 branches for purple too. Out of all these possibilities, which is the one you have the most branches? Red. That's the reason why we're going to stick with the red one. Okay? So for red, of course, this is pentane. You have 5 carbon there. And then you're going to have the 4 branches. You're going to name that, right? So you're going to have 2 and 4 methyl, right? So you're going to have 2,4-dimethyl as a branch, right? Here's the other one. You have ethyl, right? You have 3,3-diethyl. So you're going to have the 3,3-diethyl. Okay? That's how you're going to name. So you're going to do the same thing for the other one. Right? Yep. Alphabetical. E and M. Right? So that's how you're going to do it, right? So this is all about the nomenclature. So it takes some practice. So know the easier first. Right? Rule number 1, 2, 3, those are easy ones. So you're going to be very clear on that one first. Then you're going to go to the complicated one. Okay? So make sure you practice that. So before I go to confirmations, sometimes instead of the IUPAC name, that's what we are dealing whole till that time, this time, right? We use common name. So the common names are sometimes so popular that you can use this with the IUPAC name together, right? So what are the common names? So for example, if you have this branch with a 3 carbon, if it is in the middle, you're going to say isopropyl for that, right? If it is at the end, what do you call? So suppose you have like this one, 1, 2, this is 4, right? So you're gonna have, this is butyl. So you're gonna have 1, 2, 3. So if you have R over here, so this is at the end carbon, right? This is just the propyl. 3 carbon, you're gonna call propyl. If it is in the middle, second carbon, then we call iso for that. Isopropyl, right? Similarly, if you have the butyl, you have 2 possibilities. If you have the simple, this is just the butyl over here, right? So this is butyl, if it is to the end carbon. If it is on the middle carbon, then you're going to call the isobutyl. If it is in the second carbon, you have. If you have all 3 to the second carbon, you're going to call the tertiary butyl. If it is on the second, third, then going to be called the secondary butyl, right? So that's our name. So pentyl, neopentyl, going to be this one, and then tertiary pentyl, going to be this one, right? So tertiary going to be the same as butyl, except you have 1 more carbon there because it is pentyl. Right, so tertiary butyl, you have more carbon there, tertiary pentyl. Right, so these are common names. So for the IUPAC, you're going to do the same as before, it's not different. So for example, let's say isopropyl, the simple one. If I go back to number 6, this is same as this one, right? It's the same thing, right? So if you're going to do the IUPAC name, what is going to be? You have the methyl and then you have 2 ethyl there, right? You're going to call 1 methyl ethyl for that. This is the IUPAC name. Same as before, no change in that. But if you're going to write the common name, this is going to be isopropyl. That's the common name, right? Sometimes in the lab, we call common names for different reagents. That's why they are so popular, because everybody calls it the same name. So it is popular, right? That's the common name. There is no rule for the common name. But you have a rule for the IUPAC. Okay? So don't be confused there. Alright, so then we're going to go to confirmations, the next part of the chapter. For that, first we know the types of carbon atoms in the molecule. We're going to classify carbon atoms based on the surrounding atoms you have there. or based on the bonds that carbon gonna make with other atoms, right? So we're gonna call 1 degree, 2 degree, 3, 4, or you're gonna call name. 1 degree is called primary, 2 degree is gonna be secondary, tertiary, quaternary, right? What about the 5 degree? Do you think it's going to be 5 degree carbon? Because carbon is tetravalent, right? You can't have more than 4 bonds. So 4 is the maximum you can have, right? So no 5 or 6 degree carbon up to 4 degree, right? So now, if you see this molecule, you have all different types of carbon over there. Let's say the N carbon, this carbon over here. So now this carbon is going to have 4 bonds, right? So what are the atoms bonded to that carbon? So one bond is going to be, you have all single, right? So one is the carbon-carbon bond you have there. That is shown because this is the line drawing structure, right? So now the other going to be the hydrogen. So you have one hydrogen there. It's not shown. You have another, and you have another. You have 3 carbon-hydrogen bonds and 1 carbon-carbon bonds there. Okay. If you have this carbon, this is called always primary. So the easy way to remember that is, if you have 1 degree, that means you're going to have only 1 carbon-carbon bond there. That's the easy way. Okay. If you have only 1 carbon-carbon bond, all others are carbon-hydrogen, then that is called primary carbon, 1 degree carbon. Yep.
So then just to connect it to the past polar hybridizations, would that one have an sp polar hybridization?
What do you think? So you're going to have sp, sp2, sp3. Of course it's going to be sp2, right?
Oh, carbon-carbon.
Right? Correct me. Yes or no?
Yeah. sp2, right?
Nope.
sp2.
Whenever you have the, remember, I told you, if you have the single bond without any multiple bond, can be sp3 always. Okay? So do you have any multiple bond there? No. All 4 bonds are single bonds there. Always sp3. Always. Okay? If you have double bond, then you're going to call sp2 hybridization there. If you have triple bond, then you're going to call sp hybridization there. That's the easy way of remembering. Okay?
Alright, thank you.
So now, let's see the second one, 2 degree. Now you're going to apply the same concept. When you have 2 degree, then you're going to have 2 carbon-carbon bonds, not double. 2 single carbon-carbon bonds. Okay? If you see over here, you have 1 carbon-carbon, so this is carbon-carbon bond. You have another one, carbon-carbon. You have 2 carbon-carbon bonds to that carbon, right? What about the other? Of course, there should be 4, so remaining 2 are going to be the carbon-hydrogen. Right? So you're going to add hydrogen as needed to make the tetravalency. Okay? So this carbon is 2 degree or secondary carbon. Right? Now you're going to answer what's going to be the 3rd degree. Now you know, right? So if I take this carbon, you have 1 carbon-carbon bond there. You have another carbon-carbon second. You have 3rd carbon-carbon. And then 1 bond is missing, right? That missing bond is going to be carbon hydrogen bond there. So this is 3 degree. Why 3 degree? You have 3 carbon-carbon bonds there. Okay. What about the 4th one? So you can see over here, right? So this is the carbon. So let me draw the red color. So written another. So you have 1 carbon-carbon there. You have 2 carbon-carbon. You have 3 carbon-carbon. You have 4 carbon-carbon. So for this carbon, how many carbon-hydrogen bonds are missing? None. So 4 is the maximum, right? So no carbon-hydrogen bonds there. All carbon-carbon bonds. Okay. This is called the quaternary or 4 degree carbon. So this is alkane. You don't have multiple bonds there. You have all the single bonds. So all atoms are sp3 hybridized. And then you have different types of carbon atoms there. You have 1 degree carbon, you have 2 degree carbon, you have 3 degree carbon, you have 4 degree carbon. Right? So that's how we're gonna classify atoms in the molecule. Okay? So now, next thing gonna be the configurations. So we're gonna start from the rotation of carbon-carbon bond, right? What that means? If we take alkane, which is this one, right? Let's say the white spares over here, these are all hydrogen, okay? And the black one is carbon, so you have 2 carbon atoms, and then you have these 6 hydrogen atoms, right? If I draw the same thing over here, actually it is already done. So this is the molecule you have. So you have 2 carbon atoms there. Let's say carbon 1, carbon 2, just to indicate that. So this is carbon 1, this is carbon 2, and then you have all other hydrogen atoms. Okay? So what it means, rotation around this sigma bond. That means around this bond, the carbon-carbon bonded bond line, that's the sigma bond, right? Mm-hmm. What about this one? Which bond is carbon-hydrogen?
Pi.
Pi bond? I'm gonna say pi, right? If you say pi bond with hydrogen in any molecule, that's gonna be wrong.
It's sigma. Mm-hmm.
So for the pi bond, you must have the pure p orbitals. Mm-hmm. Hydrogen gonna never have p orbital. So you don't see double bond with hydrogen anywhere. So you can have the double bond with this one carbon if it is alkene. Okay, we're gonna have separate chapter for that. We're gonna deal with that. So all are sigma bonds in this molecule. So we're gonna focus on the carbon-carbon sigma bond. Okay? So now the rotation means you're gonna rotate that like this. So this whole group gonna rotate. You're gonna have the different position of hydrogen in space based on how much you rotate. Okay? So suppose you have this configuration in which this hydrogen, this carbon, carbon and this hydrogen. So all gonna be in one plane like that. Right? So that can be one configuration, right? All 4 atoms, 2 carbons and 2 hydrogens. They are in our plane. Okay? But if I rotate a little bit, like that, say 60 degree, now you have the plane of only 3 atoms. This carbon, this hydrogen and this carbon. Only 3. So this is not in a plane right now. Okay? So based on the rotation, the position of the atoms, in particular the hydrogen atoms, going to be different. Okay? So that is called this one. So let me explain this one first. So it's called the eclipse and staggered, right? So eclipse is going to be the one like this one. The 4 atoms in one plane, right? So hydrogen in single plane. So how many degrees going to be there? 0. If you have both hydrogen in the same plane, then dihedral angle going to be 0. That means you have the 0 rotation, right? So dihedral means you take this atom first in a sequence, hydrogen, carbon, second carbon, and hydrogen. If you take 4 atoms in a sequence, that's the dihedral angle. Okay? If they are in one plane, it's going to be 0. So this is called the eclipse conformation. This is the name given, right? So this is called this thing here over here. Whenever you say the eclipsed, this is the one, right? So the dihedral angle is 0. Sometimes it is called the boson angle, same thing, right? So now if you have 60 degree, so now this is 0, I'm going to rotate this 60, like that, right? If I rotate another 60, then you're going to have the same eclipse like before. So I'm going to go 120 degree far, I'm going to go half of that, about 60. Okay? If I have this, then this is called the stagger. It is 60 degree because before you had 0 degree, now I'm going to rotate to 60 degree like this. Right? So this is called the stagger. What if I go 60 farther than that? If I go 60 farther than that, now this hydrogen is going to be in the same plane with the other one. That means the other hydrogen from other side going to come to the same plane, right? So if you have the one hydrogen in one plane, that means the others are also. You have these hydrogens in the same plane, other 2 are on the same plane. This is on the same plane, right? So this is called eclipse, and the halfway to that, this one, this is called the stagger. Okay, you have 2 conformations of ethane. For butane, you have another one, but for ethane, this is the simplest alkane. There you're going to have the conformation that has 2, eclipse and stagger. Okay, good.
Are these conformations ever used on longer chains of alkanes, like the really long ones?
Don't do it, we're going to go there.
Okay.
You want to know the harder one first? Okay, let me go back. So before I go to butane, Newman projection. So sometimes this is going to be a little bit confusing, right? So how we define that? How write the structure of this molecule in the way that it's going to be easier to visualize this thingy in the structure, right? If I write this way, it's going to be harder to visualize, right? Based on how you think, you may define differently. You cannot say which atom is in which plane there, right? It is harder. So to simplify this, we draw in the systematic way, which is called the Newman projection, right? So for the same molecule, you're going to draw like this one. So this is called Newman projection. So here you can clearly see how the atoms are placed in place, in space. Okay? So now let me show you, let me clarify that to make it easier. Let's say for the same ethane molecule, I'm going to label these carbon atoms 1 and 2, right? Let's say blue and red. That will be easier to read that, right? let's say blue is number 1 from your side, so you are viewing that. So I am talking from your perspective, not mine. Okay? So see from your side, this is going to be the first carbon, you're going to see this is carbon 1. And red is going to be the second carbon, this is on the back. Okay? So now the question is how to draw this. So you're going to draw this first. Right? So when you see, you're going to clearly see the bond between carbon and hydrogen, right? So that's how, if I write with the blue color, the same carbon, right? So this blue bond over here, that is on the front, okay? So you're going to write this way. So this is the center. You're going to have 1, 2, 3 blue bonds there. Carbon, hydrogen, 3 bonds. That is on the front. This is carbon number 1. Okay? So now if you see this way, the red is going to be hidden behind the blue one. You're going to see the red one, right? So you don't write red. So you say that the second carbon is behind that, we don't see it. That's why in this labeling, you don't have number 2 there, right? Do you? No. Because number 2 carbon is hidden behind. You don't see it. So this is represented by this circle. So this circle over here, so let me write the red color. So that is red. So this circle, that's going to be for the one that is behind versus the red one. Okay? So now you're going to just draw 3 carbons on the red one. 3 hydrogens on red carbon, right? So these are red over here. So 1, and then you're going to have the 2. No, 2 is over here. And then number 3 over here, right? So red bonds are for the back carbon, right? Blue one is from the front carbon. You're going to draw all bonds from the center for the first front one. For the back one, you just keep this circle and then draw the bond after that, right? So that's how you're going to draw. The Newman projection is going to be like that. So whatever you see from the center is going to be front. So this is going to be on the front side, this carbon, right? And then whatever you have, circle, and then if you show any bond on that, like this, so this is going to be back. This one, right? That's how you're going to draw it, right? So now, after this, the structure shown over here in this projection on the slide, okay? This one. Is this eclipse or stagger?
Staggered.
Okay.
You can guess. I'm gonna clarify. So in this picture over here, so Newman projection, right? So what is the confirmation? It is the eclipse confirmation or the stagger confirmation?
Staggered.
Stagger, right? If it is eclipse, then how are you going to draw?
Doubled up.
So you're going to have that front, right? And then for the back, you're going to draw nearby that. So the hydrogens are nearby to the other hydrogen. It is close by, that is the eclipse. It is far about 60 degrees from there, going to be staggered. So the angle from one line to the other one is going to be 120 degrees, right? So to make half of that, going to be 60. That's the stagger. That's what you see in the figure there, right? So that's all about the stagger and eclipse. So now you know that. stagger eclipse, so you're gonna go through this. So now, let's see for the butane. So now butane is gonna be a little bit confusing, right? So you're gonna replace one hydrogen with CS3. It's gonna be like this. Before, I had 3 hydrogen over here, 3 hydrogen over there, right? So now I have for one carbon, the blue carbon, I have 2 hydrogens, one is replaced by CH3. Same for the red one. You have one CH3 there for the 2 hydrogens, right? So how many total carbon? 1, 2, 3, 4, butane. Okay? This is butane molecule. So now, once you have the more carbon atoms, then it's not easy like ethane. You're going to have the complicated profile. That means you don't have the simple conformations like eclipse or stagger. You have more than that. Okay? So now the question is how to define that. So for that, you're going to go through all these slides. So all are defined over here. I'm going to go to the summary. Right? So, like before, the 2 things, stagger that is about 60 degrees, like that. This is stagger over here. And then the one going to be like this, going to be eclipse, if you have the atoms in one plane, right? Or we call them slightly differently. So the one like a stagger is going to be called gauge conformation, that is about 60 degrees, right? And the one like eclipse you have, you're going to call this eclipsed or totally eclipsed. You can have different types of eclipse there. In ethane you have the same 3 eclipse, so we're going to call 1 for that. But here you're going to have different types, right? So you're going to have 1, 2, 3 actually. This is also eclipse over here, right? So now it is confusing, right? So let me clarify. Let me start with the one. Just let me show you the eclipse one only. Okay? This is one eclipse. I have the carbon, carbon, carbon all in one plane with respect to the central carbon. Okay? So I'm gonna call like this one. So 4 carbon atoms. Remember, dihedral angle gonna be based on the 4 atoms. Don't go after carbon per hydrogen. So you're gonna call 1, 2, 3, 4 is done over here. You're gonna go 5 there. So up to the 4 atoms only. Okay? So you have 4 atoms in one plane. Right? This is like eclipse before. Now if I rotate 120 degree like that, again I have these 4 atoms in one plane. This is also eclipse. Right? And then I'm gonna go 120 again. So now this is also eclipse. Right? I have 4 in one plane. Right? I have 3 eclipse conformations over here. If I go another one, the 4th one, the same as the first one. Not different. Right? So I have 3 eclipse. But out of 3, the first one is the unique one in which you have the carbon, carbon, carbon is in one plane. The second one is not like this. Second is like this one. You don't have the carbon, carbon, carbon in one plane. You have the carbon, carbon, carbon and hydrogen is in one plane. That's the second one. Okay? And then the third one, like this. Is it similar to the second one or the first one? Second one. You have the carbon, 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 hydrogen there. Right? So out of 3 eclipses, 1 is unique. in which you have the carbon, carbon, carbon is in one plane. But the second and third, they are similar. They have carbon, 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 and hydrogen in one plane. Okay? So that's why you're going to call this. So the totally eclipse over here is going to be carbon, 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 carbon. 4 carbon in one plane. Okay? But the simple eclipse you have is going to be carbon, 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 and hydrogen in one plane. The same for the other one. Carbon, 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 and hydrogen in one plane. Okay? So in my structure, this is like 1, this is like 2, this is like 3. So number 1 is like this. You have the carbon, carbon, carbon in one plane. Okay? The dihedral of carbon, 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 4 carbons is 0, one plane. But for number 2 and number 3, it's not like this. It is like this. You have the carbon, 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 and hydrogen after that. So you have the 0 angle for the dihedral made by carbon, 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 hydrogen. 2 and 3, that will be like this. Okay? So that's why you're going to say the simple eclipse and the totally eclipse. You're going to distinguish that. Right? What about the gouts? Right? Now, we are not seeing the one plane. We're going to see like a stagger conformation. So it's going to be at 60 degrees apart. So I'm going to do something like this. So I have the plane, carbon, 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 hydrogen, and the fourth hydrogen, going to be at 60 degrees, not 0. Okay? So this was stagger for ethane. You're going to call this as gouts. This one and this one. Just write the different color. So the green one over here, the green circle, this is going to be, you have, let me see over here. So that one, carbon, 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 hydrogen, that dihedral is going to be 60 degrees. Before it was 0. Right? So now you're going to have the 60 degree. You don't make on the same plane. So I am talking about this hydrogen plane over here. So it is not in plane of 3 carbons. It is 60 degrees apart from that. Right? So this is called the gouts. Now if I keep rotating that, I'm going to go somewhere in which I'm going to have this. A unique conformation in which you have 60 degrees apart, but this the heaviest group, methyl group, that's going to be the opposite side. Right? So still this is gouts. If I see the plane over here, the hydrogen is 60 degrees apart from there, but the methyl is opposite to this one. Okay? If I have that, it is called anti. This is what this is called. Let me write the purple. So this is called anti. It is like gouts. If I just rotate by 120 like this one, you see it is 60 degrees, right? But these two are not opposite, nearby, right? So this is not anti. This is gouts. To be anti, this is the requirement. If you have the methyl group opposite each other, this is called anti, right? So these are the confirmations. So anti, remember that. Totally eclipse, remember that. And then simple eclipse and gauge. So all as a result of carbon-carbon bond rotation. Okay. Now if you see the energy, so which one gonna have the least energy?
The anti.
You can see over here, right? So this is the energy, this is the lowest one. So always anti gonna be the lowest one. So by the way, for the Spartan simulation, you're gonna calculate this. I'm gonna show you how to calculate the profile. So you're gonna calculate and you're gonna compare with this one. So we're gonna do the calculation. Yep.
Isn't the last solar eclipse also carbon, 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 carbon?
Yeah, so these are the same thing. So the structure you see over here, this one, the first one, is same as the last one. There's no difference. It is like you're gonna start rotating from here, right? And then eventually you're gonna go to the same structure when you have 360 degree rotation. That's what it means. So the one cyclic, the first point and the last point in the profile, they're gonna complete 360 cycle. Okay. So this is all about the confirmations. Right? So now, okay, I'm talking about the energy. Let me finish this one. So anti is going to be the lowest one. What is going to be the highest one?
Totally eclipse.
Total eclipse, right? So this is the highest one. And then other three are intermediate, eclipse, pouch, right? So that's how we're going to see the profile. But if you see the ethane, to compare that, so we don't have the profile over here. Okay, so what's going to be the profile for ethane like this? So for ethane, you have the one lower energy, other higher energy, right? So for ethane, going to be like this. So you're going to start at 0 degree, and then you're going to have you're going to start from here, let me say 120, and then 240, right? And then you're going to have 360 there. So 0, you're going to have the higher energy, you're going to come like that. 60, so this is 60, you're going to have the stagger conformation. And you're going to go to 120, which is higher one. Come back again to the lower one, 180, and then you're going to go to 240, and then like that. So equal, right? Why this is the case? Because you have only two distinctive confirmations. So this is going to be eclipse, and this is going to be stagger. That's it, right? So if you have the third one, it's going to be same as first one, eclipse. This stagger, you have the 1, 2, 3 stagger, 1, 2, 3 eclipse. So you're going to have that type of profile, right? So you're going to calculate this one, sure. You're going to compare them. Yeah, your question.
So when we're talking about the potential energy, where is this energy coming from? Is it like the electrons that we're referring to, or
Of course.
is it?
Mhm.
Electron?
You're going to call the chemical energy. You're going to call that.
Okay. And then I had another question too. What effect does this have if it's rotating around the carbon-carbon bond like 10 to the 10 times per second?
Now I'm going to give you the homework.
Oh, okay. It's for the homework.
So for only you.
Okay.
So you're going to see the orbital, right? So if you rotate, your orbital direction is going to be different. So if you have the strain on the orbital, you're going to have the higher energy. If the orbitals are more comfy, you don't have any strain there, then be less. Right? So all are because of the bonding and overlap of orbitals.
Oh, okay.
So by the way, if you keep on asking like 10 questions, that's not good.
That's
So here's the thing, like before I used to take any questions because the class was very small, like 15, 20, something like that. Now you are 65, 70 over here. So if you keep asking questions like many questions, then what I have to do is I have to skip slides or I have to speed up explanation, something like that. So I have to finish the course, right? So in GenChem 2, you're going to have questions from GenChem 1 also for the final. So we cannot skip any chapter, so we're going to finish all the chapter up to 14, right? So what you do is you ask like 1 or 2 or 3 key questions. If you have more, come to the observe. Okay, so you can take any time you like during the observe.
Okay.
Alright, so we have 2 minutes. So now what we're going to do is cyclic alkane. So far, we have the linear chain alkane. You have 2, 3, 4, n number of carbons, right? Linearly linked together. So these are the alkanes without any carbon cycle. Now we're going to see some examples or some class of the alkane, which is cyclic. So we call the cycloalkane for that, right? So the cycloalkane is going to be carbon-carbon linkage like before, but you have the cycle of that, right? Very simple example is 3 carbon you have. Can you have cycle with 2 carbon? It's linear, right? So the simplest possible is 3 carbon. You have the triangular geometry there, 3 carbons, right? So you have the cycle of that. This is called the cyclopropane. 3 carbon is going to be propane. We already know that. It is cyclic. You're going to call cyclo before that, right? Butane with the 4 carbon. 1, 2, 3, 4. Butane. Cyclobutane. And then the pentane. Cyclopentane, right? You're going to put cyclo before that. Hexane, 6 carbons, right? And then the heptane, octane, nonane, decane, you can have any. But it's going to be cyclic, okay? So now in general, cycloalkanes have higher boiling points and melting point than the alkane homologue. So homologue means with the same number of carbon, similar carbon. What it is saying that is the cyclohexane and the hexane, 1, 2, 3, 4, 5, 6, like that. So hexane versus cyclohexane. Both have the same number of carbon. One is linear, other going to be cyclic. If you have that, the cyclic variant is going to have the higher melting point, higher boiling point. So now, if you think the reason behind that, what could be the reason? So why cycloalkane going to have the higher one? Intermolecular force, of course, right? So that's the one going to go, okay? So you're going to have the better bonding orientation when you have the cyclic. So all carbon, carbon, carbon can be exposed to carbon, carbon, carbon of the second molecule. You're going to have the better overlap between the molecule. So you're going to have the stronger dispersive force. All right. I think we're going to continue from here. Thank you.